Good morning, my dear students. Welcome back to another session on the problems on design of tension members, part 4. So in the earlier classes, we have seen the introduction to tension members, and based upon that, from the IS 800-2007 code, we have gone for some different failures of tension members under gross section yielding, net section rupture, and block shear. Like that, we have seen the formulas. Based on those formulas, we have solved some analysis problems and one design problem also for single angle section connected to gusset plate we have solved. And today we'll do one analysis problem and one design problem. Now what is this analysis problem? This analysis problem today we are going to solve is about T section, okay, connected to a gusset plate with its flange, okay, with its flange. Now I think everyone knows what is a T section, in that what is a flange portion. So in the different types of rolled steel sections we have discussed T section, okay. This is a web portion and this is a flange portion, okay. Now this flange portion connected to a what? Gusset plate. Like this they have connected with the end wells. Now what will be changed in this one? We'll see now. Okay. This is the type of problem we are going to see now. First we'll write a question. Okay. This is the analysis problem. Okay. A T section. How I am saying it's analysis problem? After writing the question I will explain you clearly. And T section ISHT, okay, 100 at the rate 200 Newton per meter is used as a what? Tension member. We are dealing with what? Design of tension members, right? Tension member with a flange connected to the gusset plate, flange connected to the gusset plate by side and end welds, okay. And the length of the connection means length of the weld it is equal to width of flange. Determine the design tensile strength, okay. Take Fy as 300 Newton per mm square and Fu as 410 Newton per mm square. So this is the question. Now for this, if I take SP6 or steel table, both are same, right? Steel table. From that, for ISHT 100, what is this 100 means? Suppose this is your what? Gusset plate. This is the T section. Now this 100 indicates overall depth. This is 100. Now ISHT 100 at the rate 200 Newton per meter means from steel table. Sorry, I have not there with a steel table at present, but I will try to place here, so you can search. So steel table, this is the SP6 chart, handbook for structural engineers, that is structural steel sections, steel sections, right? In that, this is a code book. Okay, in that we'll be going for T section. Handbook will be there, and this is also permitted for your examination centers. Okay, now first it is what? Rolled steel beams I section. It is, these are beams I sections. Okay, and these are channel sections. Okay, these are equal angle sections. Just you can download from the Google. These are unequal angle sections. Here comes the rolled steel T bars. Okay, now what is our ISHT 200? Now these are ISHT 100 at the rate 200. This is the, please try to this one. Now see this portion, ISHT 100 at the rate weight per meter, that is 20 kg per meter में 200 newtons. Okay, into 10, right? Now what is the sectional area? Now depth of section. Now width of flange. We required only 3 things. What are these things? H, width of flange BF, and the thickness of flange and thickness of web. Depth of section is what? 100 mm. Next, width of flange, it is ISHT 100, this line. Okay, this is 200. Next, thickness of flange 9 mm, and the thickness of web, this one 7.8 mm. Okay, from this you are supposed to take the values, right? Now I will keep this aside and I will write the details here. This is what we call width of flange. How much it is? 200. Okay, next this one is how much? Thickness of flange 9 mm. This is what? Thickness of web. This is 7.8 mm. So these are the details, and from this view we can see only side welds. Okay, and if I see like this at one corner, I will try to draw here. Here it will be done like this. We are seeing now this one and this one from top, and this will be in this way. Okay, I have cutted the section. So this is the given data. Now based upon this one you are supposed to solve the problem. Okay, now one more thing you can see from here, sorry to forgot, that is gross area directly available. Okay, sectional area ISHT 100, what is this? 25.47. this is centimeter square, means 2547 mm square. So these are the details. Now first condition, what? Design strength due to yielding of gross section. Design strength due to yielding of gross section. Now what is the formula, anyone? What is, one second, my pen, I am missing it. Now TDG equals to AgFy by gamma m naught. What is Ag? From the steel table or SP6, 2547 mm square into Fy is given as 300 divided by gamma m naught, it is always 1.10, right? So 2547 into 300 divided by 1.10, I will write in kilonewtons, that is 694.363 kilonewtons. This is what next one is design strength due to rupture of critical section. For that, it is TDN equals to 0.9 ANC, okay, Fu by gamma m1 plus beta into gross area of outstanding leg into Fy by gamma m naught, right? This is the formula. Now first we'll try to calculate what is ANC. What is that? Area of connected leg. What is that? Flange is connected. So that is width of flange into thickness of flange. Okay. So what is the width of flange? It is 200 mm. Thickness of flange is so 1800 mm square, right? Next, AGO. Total length is 100, but this area already covered in this flange portion. So 100 minus means H minus thickness of flange into thickness of web, means total 100 minus, if I deduct this one, I will remain with this one. This length multiplied with this thickness will be the area. So 100 minus 9 into 7.8. Okay, so it will be, sorry, 91. 100 minus 9, it is 91 into 7.8. So you are getting how much? 709.8 mm square. Okay, right. Next, first we'll write the beta formula. So beta equals to what? 1.4 minus 0.076 into W by T into, what is that? Fy or Fu? Fy by Fu into Bs by Lc. This is the formula. Okay. Now, what is this W here in this case, and what is we have to check it now, right? Now here W indicates what? Outstanding leg, that is W equals to H, that is 100 mm. And what is there in this? Bs. Now here in this case, Bs is nothing but we call as what? Shear lag width, which is equals to, how to calculate? W plus Bf by 2. This is minus Tf by 2. Why it is? Means because it is a T section, some special case will be there. Okay, for that, what is W? 100 plus 200 by 2 minus 9 by 2. So how much it will be? 9 by 2 means it is 4.5, right? 100 plus 200 by 2, it is 100 minus 9 by 2, it is 4.5, means it is 195.5 mm. Next, LC equals to what? It is given length of connection is equal to width of flange, that is BF, which is equals to 200 mm, right? Now you substitute everything in this BF. So beta equals to 1.4 minus 0.076 into, what is W? 100 divided by thickness of web, okay, into Fy is given as 300 divided by 410 into what is B? We calculated just now, 195.5 mm divided by LC is 200. If I solve this one, 195.5 divided by 200 into 300 by 410 into 100 divided by 7.5 into 0.076, 1.4 minus answer. So how much you are getting? You are getting beta as 0.70. What is beta 703, which is greater than 0.7? Okay, so you can, and anywhere it will be, definitely it will be less than beta max. What is beta max formula? We'll remind now. What is that? Fu gamma m naught by Fi gamma m1. What is Fu? 410 into 1.10 divided by 300 into 1.25. Okay, so 410 into 1.10 divided by 1.20 means this is maximum and this is minimum. It is in between this one. Now substitute here in this main formula, this formula. What values you have to substitute? So TDN equals to 0.9. What is ANC? 1800 into Fu 410 divided by, what is that one? Gamma m1, that is 1.25 plus beta 0.703 into 7 AGO 709.8, okay, into Fy 300 divided by m naught, it is 1.10. okay, I will substitute it. So I will write in kilonewtons, that is 531.36 plus this one 0.703 into 709.8 into, so it is 136. So total is how much? 531.36 plus 136.08. So 667.44 kilonewtons. Okay, now this is 694 due to yielding and 67.44 for rupture. What is the third one? Design strength due to block shear. What? Block shear. Design strength due to block shear. Now there are two formulas. If you remember those two formulas, that is TDB1 equals to AVG Fy by root 3 gamma m naught plus 0.9 ATN Fu by gamma m1. This is one formula. And what is another formula? I write here beside this one. TBD2 means 0.9 AVN Fu by root 3 into gamma m1 plus, okay, ATG Fy by gamma m naught. Okay, so we already discussed regarding what is AVG which is equals to AVN, that is area under shear, right? Next, ATG or ATN, this is nothing but area under tension, right? Now which will be under shear? Based upon the pull applied parallel to the load applied, it will be under tension, right? Now flange portion will be under tension. So here area under shear is length of weld into thickness of flange into 2, because flange is connected, so we are taking this one. Next, again here area under tension is BF minus TW, so remaining portion will be there, okay, into thickness, it will be pulled, okay. So this is the area under tension, this is the area under shear, right? Next, we'll substitute all these values in the above formulas so that we can obtain the answer. First, we'll solve TDB1. What is area under shear you got? That is 300,600 into Fy 300 divided by root 3 into gamma m0 plus 0.9 into area under tension is what you got, 1729.8 into 410 divided by 1.25, okay. So 3600 into 300 divided by root 3, so this is 566.85 plus 0.9 into this is 510, so 1077.45 kilonewtons. Next we'll go with TDB2, okay. What is TDB2? 0.9 into area under shear is 3600 into Fu divided by root 3 into 1.25 plus area under tension is 1729.8 into 300 divided by 1.10, okay. So 0.9 into 3600 into 410 divided by root 3 into 1.25, so it is 613.56 kilonewtons plus 1729.8 into 300 divided by 1.10, so 471.76, so 471.76 plus 613.56, 1085.32, okay. Now from this, the lesser value is, from these two, lesser value is this one. Now we'll write here all the three, TDG, TDN and TDB. What is TDB? 1077.45 kilonewtons, okay. Next, this is what TDG, 694.63. And this is 667.44. Now, out of these three, this value is lesser. Therefore, design strength of given T section ISHT 100 at the rate 200. Design strength of given T section ISHT 100 at the rate 200 Newton per meter under tensile strength. You have to mention under tensile strength is how much it is? 667 kilonewtons. Okay, so in this way you are going to calculate the design strength of the given T section. Okay, next we'll do one design problem. Single angle section gusset connected to a gusset plate which is used in a roof truss. Now what will be the difference in the previous class problem we done? This one is only the purpose of usage, not in the design. Design is same, but while checking the slenderness ratio it will be varying. Okay, even though it is very important. So we'll try to solve. Design a single angle section okay, for a tension member of a roof truss. So what will be the tension member of a roof truss? Main tie tension member. Okay, roof truss to carry a tensile force of what? 150 kilonewtons. The member is subjected to what? The member is subjected to possible reversible stress, possible reversal of stresses due to action of wind. So while discussing about the theory regarding the tension members, maximum slenderness ratio values we have seen. Okay, if a member which is always under tension will have a maximum slenderness ratio value of 400. Next, a member in which reversal of stresses occurs because of wind, it is having a maximum slenderness ratio value of 350. And a member in which reversal of stresses occurs not because of wind load, it is having 180. So you have to remember those values while calculating the slenderness ratio. Okay, next, the length of member is 4 meters. Fy 250 Newton per mm square. Fu 410 Newton per mm square. And effective length of weld is 200 mm. So this is the data given. Okay, now in the question it is not mentioned, it is as a factored load. So now solve it. So factored load equals to how much? 150 kilonewtons axial load into 1.5. So it will be around 225. half of it to be added, right? 225 kilonewtons. Now assuming permissible tensile stress, how much it is? FTD equals to 0.9 into Fi. So what is that? 0.9 into Fi is given as 250. So it is 225 Newton per mm square. Now gross area of section required how much? A equals to 225 kilonewtons. If I multiply with 10 power 3, it will be newtons divided by stress. So it is around 1000 mm square. This much of area is required. Okay, so what we do is, while taking the section from the steel table, we will be increasing, okay, by 10 to 25%. So increase area by 10%. So what it will be? 1.1 into 1000. Now to this area from steel table you have to take. Now in this problem they have not at all mentioned regarding what? Take equal or unequal angle, like that they have not mentioned anywhere. So we'll try to take area 1100 mm square, right? So see, this is the area, this is 11.37, 125 by 75 by 6 mm. Okay, so see how I am taking. First I am taking the area 11.66, or we want 1100, so 1166 mm square. Okay, so from steel table choose ISA 125 by 75 by, what is this, 6 mm with an gross area of how much? 1166 mm square. 1166 mm square. Okay, now first design strength due to yielding of cross section. Okay, so what is the formula? TDG equals to AGFI by gamma m naught. AGFI by gamma m naught. What is AG? 1166 into Fi is given as 250 divided by 1.10. So 1166 into 250 divided by 1.10. So it is 265 kilonewtons, right? Okay, next, what is another one? Design strength due to net section rupture. net section rupture. What is the formula? That is TDN 0.9 ANC FU by gamma M1 plus beta AGO FU by, so this is FU, this is FI, gamma M0, right? Area of connected leg. Now when I am taking unequal angle section, longer leg will be connected mostly. Okay, so connected leg 125 minus 6 by 2 into 6. So 125 minus 6 by 2 means 122 into 6. It is 732 mm square. Next, AGO. What is outstanding leg? 75. So 75 minus 6 by 2 into 6. So 72 into 6. It is 432 mm square. Next, well, what is the beta? Beta equals to 1.4 minus 0.076 into W by T into Fy by Fu into Bs by Lc. So W is what? Outstanding leg. So everything I know. 1.4 minus 0.076. What is W? Outstanding leg length 75 by thickness is what? 6 mm into Fi is 250 divided by Fu is what? 410 into 75 by effective length of the weld is given as 200. Okay, so 0.076 into 75 divided by 6 into 250 divided by 410 into 75 divided by 200. 1.4 minus 1, so 1.18. Beta minimum is how much? 0.7. Beta maximum, you have to check it now. That is Fu gamma M0 by Fi into 1 gamma M1. 410 into 1.10 divided by 250 into 1.25. Okay, 410 into 1.10 divided by 250 into 1.25. So it is 1.44. So beta value is in between 0.7 and 1.44. Now everything you got, substitute here in this formula. So TDN equals to 0.9 into ANC connected leg length 732 into 410 divided by 1.25 rupture, okay, plus beta 1.18 into AGO 432 into 250, okay, divided by 1.10. How much it is? 0.9 into 732 into 410 divided by 1.25. So 216.086 kilonewtons plus 1.18 into 432 into 250 divided by 1.10. So 115.8 kilonewtons, which is total come together 216.086 plus 115.8. So 331.886 kilonewtons. So this is what? Design strength due to net section rupture. Okay, next we'll see due to block shear. That is design strength due to block shear. Now we'll write the formulas first. TDB1 equals to, okay, what are these? AVG F5 by root 3 into gamma m naught plus 0.9 ATN FU by gamma m naught. And what is this? TDB2 0.9, okay, 0.9 AVN F, this is Y means this is U by root 3 into gamma m1 plus ATG Fy by gamma m naught. Reverse, this will be gamma m naught means gamma m1, gamma m1 means gamma m naught. 0.9 here comes for tension, it comes for shear, okay, that you have to check. Very easy to remember the formulas, okay. First, area under shear AVG or AVN, okay, area under shear. Now what is the length of the weld given? LC, length of the weld is given as 200 into 2 into thickness, so 200 into 2 into 6 mm, 2400 mm square. Next, area under tension ATG or ATN equals to what? Okay, so connected leg length into thickness, okay, so it will be around 125 into 6, it is 750 mm square. Okay, everything I know, I can substitute here in the TDB1. So AVG is how much? 2400 into 250 divided by root 3 into 1.10 plus 0.9 into, what is ATN? ATN, area under tension, right? 750 into, what is FU? It is 410, I think, right? Divided by 1.25. So 2400 into 250 divided by root 3 into 1.10. Each term separately I am calculating, okay, for easy convenient. 314.9, okay, kilonewtons plus 0.9 into 750 into 410 divided by 1.25. So 221.4 kilonewtons. For all together, how much it will be getting? So 314.91 plus 221.4. So how much it is? 536.31 kilonewtons. Next, TDB2. This is 0.9 into ATG, area under tension. What is that? Oh, sorry, AVG 2400 into 410 divided by root 3 into 1.25 plus, what is ATG? 750 into 250 divided by 1.10. Okay, so 0.9 into 2400 into 410 divided by root 3 into 1.25. Okay, 409.041 kilonewtons plus 750 into 250 170.454. Okay, 170.454 plus 409.041. So how much you are getting? 579.495 kilonewtons. Okay, now we'll summarize all the values of, that is what, TDG, TDN and TD, what is that, B. Okay, while summarizing, if you see back to your previous two calculations, area under grass is 265 kilonewtons, Next one is 334.886 kilonewtons, and this from here TDB will be what? Lesser of TDB1, TDB2. So this one is the 536.31 okay kilonewtons. Now what you have to write the statement here is the design tensile strength obtained for the section chosen. You have to write for the section chosen. Why we are writing chosen? Because we have designed it, right? So the design tensile strength obtained for the section chosen 125 ISA Indian standard 125 by 75 by 6 mm is how much? This one. Lesser of these three, right? So 265 kilonewtons, which is greater than 225 kilonewtons, means hence our section chosen is satisfying the load, means it can bear more than 225 kilonewtons. Actually axial load is how much? 150, but we have factored it and we have designed it, and after that we have chosen one section and calculated its a design tensile strength. That value, it is greater than 225, means hence our section chosen is sufficient. Our section chosen is sufficient. Now whether this problem completed or not, means I said no, because you have to check it for under slenderness ratio. For that reason only they have given some statement of reversal of stresses may occur due to possibility of reversal of stresses occurs due to wind, and they have given the length like that. For that reason you have to check it. Okay, now this is important. Check for slenderness ratio. Now for chances of what? Reversal of stress due to wind, means what is the maximum slenderness ratio? Mean slenderness ratio should not be greater than 350. This is the condition. Now what is the effective length given? 4000. And next for ISA 25 by 6 mm, right? We have chosen next page. See, this is for ISA 125 by 6 mm. What we are looking for actually? Radius of gyration. Okay, what is that? 125 by 75 by 6 mm means first line. In this first line, so how much it is? So this line, this is 40 and this is 21. Okay, so I am choosing 21 minimum, R minimum. So how much it is? So 190. Okay, which is less than 350. Hence our section chosen is satisfying all the conditions. Thank you for watching my video. Please do watch more videos for more problems on these chapters.